Welcome everyone to the second lecture of week number 13, and as it's week number 13 and we were discussing chapter 6 entitled Autocorrelation, and it was the third part of the textbook. Regression Diagnostic is the title of the third section of the book. So let me show you the contents of the week 13. In week 13 we were supposed, in the first part and in the second lecture, in both lectures we were supposed to cover autocorrelation, and we started with the basic concepts of autocorrelation, and then we have to talk about test of autocorrelation, graphical method of detecting autocorrelation, Durbin-Watson statistics, and BG test. This is the content which we have to cover in week number 13. Now, in previous lecture, that was the first lecture of this week, we talked about some basic concepts. In this basic concept, we covered the concept of covariance and correlation and their measurements. So we have a detailed discussion of what's the difference between these two and how these are measured. Then we talk about how covariance and autocorrelation are linked or can be linked with the covariance and correlation concept, and how we can measure autocorrelation. And for this particular topic, we focus on autocorrelation measurement, and we said it's measured through autocorrelation coefficient, and it's represented by rho. Then we talk about the causes of autocorrelation, and we mention number of causes of autocorrelation. We'll show you in a minute what are these causes. Then we finally did discuss the consequences of autocorrelation, and we also had some discussion on the spurious regression. Today lecture will be more applied side compared to the previous lecture of this week. However, before going there, let me quickly give you an overview of the topics which we have covered last time. So autocorrelation happens when there is a violation of the classical linear regression model assumption. One of the assumptions says that the error of the observation, the successive error value, should not be correlated. However, when these successive value get correlated with one another, we say that it's a case of autocorrelation. More formally, we say the correlation between two successive error term ui and uj, given that x values when I and j are not equal to each other, this covariance between the successive value ui uj given x should be equal to 0 to meet the assumption of OLS. If this covariance is not equal to 0, we have a problem which we called autocorrelation. Now, we did discuss in detail what are the major causes of autocorrelation. We mentioned 6 reasons for having autocorrelation in the data. These were inertia, specification bias, COVID phenomena, lags, manipulation of the data, and then on stationarity. We had a detailed discussion on it, and at this stage I don't feel like to repeat all that discussion again. For interested student, I would strongly recommend to check the previous lecture for detail on these. Then we move to the consequences of autocorrelation, and we mentioned a number of issues with autocorrelation, but our main concern was that because autocorrelation caused the standard error underestimated and is no more efficient, so the OLS estimator are no more blue, and when it's no more blue, we can't trust our hypothesis testing mechanism, and even if our sample size is very large, so that make it a very serious issue. We also did discuss that when there is a problem of autocorrelation, we may end up finding relationship among variables which actually are not, they are just moving together through time, so without having any dependency on one another. So we had a number of examples in our discussion as well in the previous lecture. So today we are going to run a regression model before proceeding further to have a case study, and then we are going to see the remedial measure and applying that remedial measure to fix that problem of autocorrelation in this particular model. So the model which we have. I will name it as a practical task 13.1, and we are going to discuss autocorrelation using Eviews. So first of all, you need to download the data from your LMS. That's the autocorrelation table. It's provided, so download that data. Viewers can download their data from the playlist. There is a link in playlist. You can download the data from there as well. So the data cover USA for period 1947 till 2000 on the number of variables. These variables include consumption, real disposable personal income, real wealth, and real interest rate. Now please note that these four variables are in real terms, or in other words, these are adjusted for price changes or inflation. So we have to run a model in which consumption is being modeled as function of real disposable personal income, the real wealth, and the real interest rate, and we have to run this model in double log form. So in very simple word, we are modeling that consumption of today, that's the consumption in period T, is function of the real disposable income in period T, very same period, and then the real wealth again in the same period, and then the real interest rate again in the same period, and with the standard error term. So now this is the model which we have to estimate in Eviews, and we have to save the results for discussion. So moving towards the further Eviews analysis, so I would request all the viewers and also my students that please pause the video, go ahead with your analysis, run this model, obtain the data, run this model, and then have the output, and then proceed for the next discussion. Let me switch to my Eviews file to run this model. So this is the Eviews file, work file, and I have all the variables here available. And as you can see, I have the consumption, I have the disposable personal income, I have the real interest rate, and I have the real wealth. There is a variable time and year as well. We don't need that, so I will just keep it without any disturbance. So now I have to regress consumption on the real disposable income, real wealth, and the real interest rate. So I will select the dependent variable real consumption, going to regress on real disposable income, real wealth, and real interest rate. I will open these variables as an equation. As you can see, this is open as equation. So I will bring C at the start as always to make it specification as shown per model. Now we have to run this as double log model. So I will take log of consumption, then I will take the log of disposable income, then I will take the log of wealth, and real variable real interest rate is without any log, so we will keep it as it is. And when I press OK, the model has been run, and as you can see, the result, log of consumption is being regressed on log of disposable personal income and log of wealth, all variables being expressed in real terms. Okay, so now I will switch to the slide again to discuss it. So now once we have the output of the Eviews, what we do is this is the output. I bring it here from Eviews, and first of all, we can look into the signs of the variables, although it's not the point of discussion here, but we can just look into the sign. You can see clearly that disposable income and consumption has a positive sign, indicating when the disposable income increase, the consumption increase. Similarly, when the wealth increase, the consumption increase. That makes perfect sense. And then when the real interest rate increase, the consumption decrease because the negative sign, and it also is as per the standard economic theory. Please pay attention to the interpretation in terms of specifically quantifying them. It's a double log model, so the coefficient having log values will be interpreted as a percentage change. So now, as far as the OLS method is concerned, if we assume that all the OLS assumptions are met, we can say that the model is an excellent fit, because we can see here that the R square value has been really high, and you can also see that all the coefficients are statistically highly significant, with F statistic also very highly significant. So all this is indication of a perfect fit or an excellent fit or the something you would really love to have. So that's if we assume that all the assumption of OLS is met, so this is a perfect fit. However, we should keep in mind that this data is a time series data, and I keep on telling you that in past as well, the time series data time series data do suffer from autocorrelation. So we have to check for autocorrelation. So for autocorrelation, in presence of autocorrelation, if let's say we suspect that there is autocorrelation, then we cannot trust this excellent results anymore, because when in presence of autocorrelation, you can't trust these t statistics or the standard errors and t statistics and all these values. So because of that reasons, we have to check for autocorrelation before trusting our result and before properly interpreting it. So now we are going to discuss the detection methods of autocorrelation, and as you saw that we run a model, now we're going to check if there is a problem of autocorrelation in our model. So to start with, there are a number of ways through which we can check autocorrelation. So the procedure for me to introduce you to these methods would be that I will be discussing the theory and then we'll be applying the method. So first of all, I will be discussing the methods. I will list all the methods and then we go for discussing it one by one. The first method through which we can detect autocorrelation is the graphical method. So we are going to discuss the theory of graphical method and then we are going to apply this method. The second way of testing autocorrelation is the run test. Then we are going to talk about Durbin-Watson statistic test and its application. We are also going to discuss Brush, Godfrey, BG test and its application. Now you should note that the graphical method is an ad hoc method, not a very standard procedure. Furthermore, run test is not a standard test and it's not provided in many software. So I will be discussing these in lesser detail. However, the rest of the two tests, Durbin-Watson statistics and Brush, Godfrey or BG test is available in most of the software. So we are going to discuss the theory of these tests in much more detail, and also we will see the application and interpretation of these two tests in more detail. So let me start with the graphical method first. So the graphical method is pretty straightforward. Before discussing the theory, you should keep in mind that the problem of autocorrelation is associated with the relationship among the successive value of the error terms. So we need the value of error term to see if these values are correlated over a period of time. So the problem is we don't have the original values of the error term, so we use the forecasted value of the error term as a proxy for the original error terms. So the forecasted value can be obtained by first running the model, and then we can plot these values chronologically or against the time. So we can plot the forecasted value of the error term chronologically, or we can also generate a plot in which we plot the forecasted value in period t of the error term against the lag values of the residual. You already know what is lag value. It's the value of the same variable measured in the previous period. In our previous lecture, I talked about it, so I wouldn't repeat the whole theory here again. But in Eviews, it's very easy to calculate or to obtain the lag value of a variable. I will show you that in Eviews section. So now once you have these two plots, if the error terms are correlated, so there will be some patterns in these graphs, and in principle, if there is no autocorrelation, we should get these graphs without having any pattern, or the error term should follow randomness. But if there is a pattern, we should suspect that there is a problem of autocorrelation. So now let's move to the graphical method application in Eviews. So this is the practical task 13.2. Again, you will need the same autocorrelation data which we have used to estimate the model. You have to run the model, the double log model, which we just did a while ago, and then to apply the graphical method, you have to do following two graphs have to be generated. As I told you, residual graph over a period of time, and then residual in time period t against residual in time period t minus 1. Please do note that these are the forecasted residual values, because it's not the original residual values, it's unknown, it's from the population, so we don't know that. So once this procedure for both graphs is applied, you get these two graphs. Now let me show you how you can generate actually these graphs in Eviews. This is shown on next slide. So let me move to the next slide. Let me show you. For generating the residual graph over a period of time, you have to run the model first, the double log model as was run earlier. Then you go to generate residual series and save it as a residual. For a residual plot, all you have to do is to open the residual saved series, open it, double click, open, it will open up, and then go to the view of that group of that residual data, go to the view, and then go to the graph, and with all default press OK. So you can get the graph of the residual over a period of time. You can freeze that for discussion. Similarly, to plot the residual values against its lag value, first of all you will need to generate a variable. You need two variables, the lag values as well. So first you run the model, the same standard model, then you generate the residual series and save it as a residual. Now you need to create the residual lag value, so I named it as a residual underscore lag, and it's a standard procedure. You go to object generate series and you write the equation residual underscore lag 1, that's the name I gave it, and it should be equal to residual, and within bracket I wrote -1. So that residual -1, this residual -1 shows to ask Eviews to generate a variable, a new variable, residual underscore lag 1, and it should be equal to the first lag of the residual. So once I generate this lag value of the residual, the next step is I open these two variables, the original forecasted residual value and the lag residual value as a group, and then I go to the view, and then this time I go for scatter graph rather than line graph, because now I have two variables, and with all default setting I press OK. But before pressing OK, I would like to fit a regression line to it as well. So under the detail, I can select the regression line option and then press OK. So a line will be fitted as well to that scatter plot. So that would give me a pretty good idea. Obviously, then you freeze this graph for discussion. So freeze the graph for discussion. Now before going for the output, let me show you how we can do that in Eviews. So this was the model which we run a while ago. This is the double log model which we have run. So now we need to generate the graphs of the residual, the residual over a period of time, and then the residual forecasted value graph against the residual lag value. So first I go to proceed to generate the residual graph. I need the values of residual. I don't have that. So first I will go to forecast. I will go to proceed, then make a residual series. Here I will select ordinary. Here I will name this as a residual. So this will generate a residual series. So now I got a residual. This is all residuals. So to plot them chronologically, all I have to do is I will go to the view. I will press graph, and I leave everything as default. So this gives me residual plot over a period of time. We will discuss this output shortly. I will freeze it. Then to plot the residual against its lag value, I need to go to object, generate series, and now I will write lag residual 1. This should be equal to residual and within bracket -1. So it will take the first lag. Press OK. So I got lag residual as well. Now I will open lag residual and residual open as a group. And then I go to view, graph. This time from specific I select scatter plot, and from detail, the fit lines here in detail, I give regression line. And when I press OK, I got this graph. So now you can see we have two graphs, one with residual over a period of time and the other with residual against the lag value. We can switch the axis, but it wouldn't make a big difference. So let me switch back to the interpretation part now. So now residual over a period of time look like this, and the graph of residual and residual lag look like that graph. Now here you can see very clearly, especially from the residual against the residual lag value, that it shows a pattern. And you can see here a linear upward sloping line could be fit to these two values. So what does it indicate? It's an indication of autocorrelation. So that's the graphical method, and the conclusion is the residual plot over time shows a pattern that may suggest correlation among error term over a period of time, but the second graph of plot of residual at a time t against the residual at like time t minus 1 also with the regression line clearly suggests residual being positively correlated over a period of time. So this is one indication of having autocorrelation in our data. So moving back, we were discussing the graphical methods and its application. So now we learn that the graphical method, there are two ways of looking autocorrelation through graphical method. The first is to plot the forecasted residual value over a period of time or chronologically, and secondly the residual against the lag value of the residuals. And in both cases, if the graph shows the pattern, it will be an indication of the autocorrelation in the data. Now the second test is run test. So we move to the run test, the theory of the run test. So let me go there. The run test, as I already mentioned, that the run test is not a very popular test among the researchers. So not all the econometric software do mention this test. So I will be brief on the theory part, and I'm not going to recommend you to apply this test, so that's why I'm not applying it either. I will just tell you the procedure in case you want to apply it. You as a student need to know that there is a run test that do exist and can be used for autocorrelation testing. So to start with, run test is based on sequence of forecasted values of error terms. Normally when we have no autocorrelation, the error term follows a random sequence. So when you run a model, when you estimate its forecasted residual or error terms, the successive values of error terms are supposed to be not correlated. So in absence of no correlation among these successive values, you would expect them to follow a random sequence. However, sometime you may come across a case when there is a positive sequence of the forecasted residual term followed by a negative sequence of the forecasted residual term, or vice versa. If that kind of pattern do exist, that could be an indication of the presence of autocorrelation. The run test is based on the following of such sequence of negative and positive forecasted value of the error terms. And to use the technical terms of run test, this sequence is called run. So before telling more about the theory and how this test is applied, let's consider a hypothetical scenario and let's apply this test to some hypothetical examples. So consider 40 observations for which we run a model and we forecast their error terms, and then we see that the error terms, some values are positive and some values are negative. So I'm going to use the plus and minus signs for the positive and the negative residual terms respectively. Then what we can do is we can form a sequence of these positive and negative values. As you can see it here, there are 3 sequences, so that shows that the first 9 values of the 3 sequences are negative, followed by the positive 21 residual forecasted values, then positive, then again 10 negative forecasted value of the residual terms. Now you can see here there are 3 sequences or 3 run from this 40 observation with 9 positive, 9 negative, 21 positive, and then 10 negative again. Now the relevant question for the run test is that we have to see if these 3 runs are too many or too few for these 40 observation of the data while expecting the run to be random. Or in other words, if we say that the error terms are random, then we have to know that whether the 3 runs which we are getting for these 40 observation, is it too many or is it too less? And based on that we would say that okay, what is the number of runs? If that happens, we can call it that the errors are following a random pattern. So in general, if there is too many runs, this will indicate that the residual change signs frequently, and that's the indication of a negative serial correlation. And if there is too few runs, we may suggest that there is a positive autocorrelation or autocorrelation. Or we can check also if the pattern is random, and we then decide, or we can conclude that there is no autocorrelation. So how we do all that? We do that through constructing a confidence interval for these number of runs. The procedure is straightforward. You will need a number of formulas to apply, and then you can construct a 95% confidence interval for that. So this is the formula for confidence interval. The probability of the probability of the this is the expected value or the mean values of runs, and then minus 1.96 multiplied by the standard error, or the standard error of the run, and this is the mean. So you can obtain ER and sigma R values from these 2 formula, and you can plug in this with mean minus 1 standard deviation and mean plus 1 standard deviation, and the R value should lie between these 2. What is R? R is the number of runs. So let's say we have 3 runs here. This will be 3, and then you have n1 for the positive number of residual value and n2 for the negative value. So you plug in n1 and n2. So that's the number of positive and the number of negative divided by the number of runs, the total number of observation plus 1. So that make it this is 21 positive and 19 negative. So you multiply 21 into 19, and then you multiply it with 2, you divided it with 40, and then you add plus to it, so that will give you the value of ER. And then similarly you plug in n1 and 2 values in the second equation, and then you plug in that in this confidence interval formula. So you get a confidence interval, and your value, if R value is within this interval, we trust that the error terms are random. If it's out on one side or the other side, we may suspect that there is a problem of a positive or a negative autocorrelation. So that's the theory of the run test. And as I told you, we are not going to apply this test because it's not built in the Eviews, and it's not very popular among the researchers, so I will be just skipping that. Now moving back to the detection of autocorrelation and its application in Eviews, we already discussed the graphical method and the run test. Now we are moving to the last two methods, which I mentioned as being the most important, popular among the researchers. So I will start with the Durbin-Watson statistic test first. Then we are going to apply that in Eviews. Then we do BG test, and then we go for its application in Eviews. So Durbin-Watson statistic test. Let me start with the theory part. So the Durbin-Watson statistic test could be better understood if we start with considering a regression model of a very simple nature, in which we regress y variable measured in period t on one explanatory variable xt, whereas a constant term b1 is included in the model, and then there is an error term, and all these variables are measured in period t. Now we assume that the error term is correlated with its previous value, or in other words, there is a problem of autocorrelation in this model, and the error term in period t is linked with the error term in the previous period, or it's the correlation of order 1. We call this kind of condition the parameter rho, as we already discussed, that is the measure for autocorrelation between the error term and it's the adjacent error term or the previous period error term. You should know that this equation 2 shows the correlation, the autocorrelation of order 1, or this is called AR1 process in terms of autocorrelation terminology. We call this AR1 process. You could also have AR2 process, in which we can add another term to this model by adding more values of rho and rho 1 and rho 2, ut minus 2, and so on. So you could have AR2, AR3, ARP processes, but for time being we are considering only AR1 process, in which error term is linked with the successive value only, the first successive value only. Now the Durbin-Watson statistic test is while considering that there is a first order autocorrelation, or if there is AR1 process, then the Durbin-Watson statistic test the following hypothesis. Its null hypothesis is that there is no autocorrelation or no serial correlation, versus an alternative hypothesis that there is a problem of autocorrelation, or there is an existence of autocorrelation. If there is no autocorrelation, the rho term will be 0. Look into this model. If rho is statistically significant, not significant, so the rho would be 0. So this whole term becomes 0. ut is equal to vt, or there is no autocorrelation. It's a random term. We presume that this vt follows no autocorrelation, and it's free. It's a random variable. Then we says when there is a problem of autocorrelation, when we reject h0, in that case rho is not equal to 0, and we have a problem of autocorrelation in our data. Then how we check this hypothesis, how we check these two hypotheses. So let's say we have a data on y variable, we have data on x variable, and we know that there is a first order autocorrelation. But how we can check that these two hypotheses? For that we need a t statistic. So the Durbin-Watson t statistic is given through this formula. This formula may sound very complex, but the good thing is that you don't have to memorize it, and you don't have to calculate manually these values of D statistic. The softwares do provide these values as a standard output for the regression output. When you run a model, it is provided with that, but you need to know that how it's calculated. So if you look at this formula, there is two error term ET and error term TET minus 1, reflecting the residual value in period T and in period T minus 1. Now this model D statistic value is based on the original population error terms values. However, these values are never observable, so instead we use the predicted values of the residual terms or error terms. One more thing, this D statistics and the correlation, the autocorrelation coefficient also have a relationship, and it's also some mathematical works involved, and again we don't need that mathematical work being involved in it, but we need to know that there is a relation between the Durbin-Watson D statistics and the autocorrelation coefficient rho, and that relationship could be written as dw is equal to 2 into 1 minus rho. Now why we need that equation, the second equation, given that we already have one equation through which we can calculate D value? The reason for that is that this second equation is more convenient for interpretation purpose, and it has some more application as well. So now having this second equation dw equal to 2 into 1 minus rho, there is very interesting properties associated to this equation. Let me put that formally. We already know that rho measures the autocorrelation between the two error terms values, and we know that it range between -1 and +1. So if we plug in these values one by one in this equation, we get the range for Durbin-Watson D statistic. For example, if the value is -1 for rho, so if I plug in -1 in this equation, Durbin-Watson D statistics would become this would become -1, so minus become plus, or Durbin-Watson become 2 into 2, and that will give to me values of 4. Similarly, if I plug in +1, so that become 1 minus 1, and that become and it gives me a 0 value, and so on. So I can calculate the different value. So this gives me the range for Durbin-Watson. At the maximum value, Durbin-Watson can have 0, minimum value could have 0, and maximum value it would have 4. Now another property of this equation is that we can find out if there is a positive autocorrelation, then what would be the value of D-Watson D statistic. If it's negative autocorrelation, then what would be the value of the D-Watson D statistic. So to put it, when rho is 0, it means that the error terms are not correlated at all. So if you plug in rho is 0 in this D-Watson equation, we get dw equal to 2. So when we obtain dw equal to 2 or close to 2, that means there is 0 or no autocorrelation in our data. So you instantly know, if you plug in the rho value equal to 0, you instantly know that okay, rho 0 is the case when there is no correlation among the residual terms, successive value of the residual term. So you get dw equal to 2. Similarly, when there is a perfectly positive and a perfectly negative autocorrelation between the error terms, you get -1 or +1. You can plug in and you can find if dw, what is the possible value for dw when it's a positive or when it's a negative autocorrelation. It's mentioned here when there is a p is equal to +1. So when you plug in +1, you get dw equal to 0. So that shows that when dw is close to 0, there is a positive autocorrelation. Similarly, when we put -1 in this equation, the dw values become equal to 4. So that's an indication that there is a negative autocorrelation. Now please keep in mind that you will not be getting exactly 2, 0 or 4 values. Rather you will be getting a closer value to 2, a closer value to 0 and a closer value to 4, and accordingly we do then decide, or we may suspect that if there is a no or positive or negative autocorrelation. So now let me show you the critical regions for Durbin-Watson D statistic. There are separate values for the upper and lower bound. These are the thresholds through which we can define the upper and lower bound for D statistics. Durbin-Watson prepare tables that give the lower and upper limits of the D statistics for a selected number of observation and a number of regressors, and for 5% and 1% level of significance. We should know that there is a separate tabulated values by the same way we have it for Z statistic or T statistics or F statistics. We also have values for the D statistics, and these were tables prepared by Durbin-Watson for a fixed number of observations and for different level of significance and a number of regressors. Before showing you the table, I would love to show you the graphical representation of the critical region for the D statistic value, just to strengthen your concept of understanding this lower and upper threshold values for rejecting or accepting the null hypothesis, which says that we have no autocorrelation. So to start with, we can think of the D statistic value range, that range between 0 to 4, and we think of the value 2. These are the three extreme values. 0 shows the case when we have a perfect positive autocorrelation, and any value, if we have D value equal to 0, this shows perfect positive autocorrelation. If D value is close to 0, that also shows positive autocorrelation. Similarly, the value of 2 shows a case of no autocorrelation, and if a value is close to 2, that also shows no autocorrelation. Then 4 shows a case of perfect negative autocorrelation, and a value close to 4 also shows a negative autocorrelation. Now the real question is that, okay, we know that 4 shows perfect negative autocorrelation, and also we know that the value close to 4 shows negative autocorrelation, but how much close? Is it this close or this close or this close? So what is the range of closeness? Similarly, what is the range of closeness for 2? Similarly, what is the range of closeness for 0? So that range are defined through this DL and DU. So how is it done? We take the lower and upper limit. So this is the upper limit, this is the lower limit. So now this defines the ranges for the closeness, the more close or the far more. And then you can think of defining these ranges here as well. Once we have the value of DU and DL, we can calculate the value of 4 minus DU and 4 minus DL to define 2 more ranges. Now we have more ranges. Now this is the graphical representation. We say when the value range between when the value is 2, there is no autocorrelation, and when the value is within the range of DU and 4 minus DU, again we say there is no autocorrelation, and we do not reject H0, which says that there is no autocorrelation. We do not reject H0, and we says that there is no positive or no negative autocorrelation within this range. However, if the values is within this range 0 to DL, we reject H0, that there is no positive autocorrelation, but we do not reject H1, which says that there is a problem of positive autocorrelation. Similarly, in range 4 minus DL and 4, we have the range when we have a value within this range, this shows that there is a negative autocorrelation. And then there is some range left between these two intervals. We call this inconclusive zone, or a zone about which we can't decide if there is a issue of autocorrelation. Okay, so that was more or less the graphical representation of the critical region of Durbin-Watson D statistic test. Now let me show you the table of the Durbin-Watson D statistic critical values. This is the small portion of the values they have estimated, prepared for the critical region for the D statistic value. Now moving further, we can think of the Durbin-Watson D statistic method is based on number of assumptions, and this test is good only if these assumptions are made. One first assumption is that the regression model should include an interceptum. That's pretty standard. This is also assumed that the regressors are fixed in repeated sampling. That's also consistent with one of the assumptions of ordinary least square method, which says that the explanatory variable having a fixed value in repeated sampling. So these two are pretty standard and simple assumption, don't need further explanation. The third assumption says that the error terms is follow the first order autoregressive or AR1 scheme. Now this is a very important assumption. This assumes that the Durbin-Watson D statistic is based on assumption that the error term is only correlated with the first leg value only. So in other words, Durbin-Watson D statistic check for the first order autoregression only. It can't check for autoregression of order 2, 3 or higher. So that's a very important assumption. Then the fourth assumption is that the error term is normally distributed, and the fifth assumption is that the regressor do not include the leg value of the dependent variable. This is also a very important assumption, the last one, which says that when you model your data, if you have one of the explanatory variable as the leg value of dependent variable or y variable, then you can't apply Durbin-Watson D statistics, or one of this assumption will be violated while applying D statistics in this particular case. So how this method work? Let me highlight the procedure step by step, and then we are going to apply that in Eviews. The procedure is as follow. First of all, we run the OLS regression model and we obtain the residuals as a standard procedure. Then we compute the D from the formula. So we already have the formula of the D statistics is equal to 2 into 1 minus rho, or the other formula in the forms of summation of error terms. So we do that. Then we calculate the upper and lower bound for the given number of sample observation and the explanatory variables. We look at the DL and DU. We define the critical region and we follow the following rules. T is equal to 2 or close to 2, then there is an evidence, no evidence of positive or negative autocorrelation. D is 0 or close to 0, we have a positive autocorrelation. D is 4 or close to 4, that's the evidence of a negative autocorrelation. As I explained it from the graph a bit more in detail, keeping this graph in mind on the very top corner, right corner of this screen. So the decision rules as per graphs are as follows. If D is less than DL, there will probably evidence of positive autocorrelation, and then if D is greater than DU, so if D is greater than DU, there is a probably no evidence of positive autocorrelation. When if DL is less than D is less than DU, then no defined conclusion about positive autocorrelation. Similarly, if DU is less than D is less than 4 minus DU, that's the probability there is no evidence of positive or negative autocorrelation. On fifth, we says that if 4 minus DU is less than D less than 4 minus DL, so no definite conclusion about negative autocorrelation. And finally, if 4 minus DL is less than D less than 4, there probably is evidence of negative autocorrelation. This is something you can't memorize. All you have to do is to keep this graph in mind, and then you can write all these statements by yourself. So this is also important to note that d values always lies between 0 and 4. The closer the value is to the 0, the greater is the evidence of positive autocorrelation. The closer it's to the 4, the more stronger is the evidence that it's a negative autocorrelation. If it is close to 2, this is evidence of having no autocorrelation. Now going for the application of the Durbin-Watson D statistics to our data. Okay, so once we have the Durbin-Watson test theory being discussed in detail, it's time to apply the test. The good thing about the Durbin-Watson test is that it's very easy to apply. The bad thing about the Durbin-Watson test is that its theory is too much. So to apply the Durbin-Watson test, this is a very straightforward task. All you have to do is to run the model and Eviews as a standard output, and some other software as well as a standard output of regression to provide the D-Watson D statistic value. So if you can see on the right side of the slide, you can see the consumption log being regressed on the log of the dependent on the disposable personal income and the wage and the in real interest rate. All these variables are in real terms, and at the bottom of these results you can see here the value of Durbin-Watson being 1.2, and as discussed a while ago that this value, if it's close to 2, then it shows that there is no autocorrelation. If it's close to 4, then it shows a negative autocorrelation. If it's close to 0, then it shows a positive autocorrelation. So now its value is between 2 and 1, so it is kind of indicating either positive autocorrelation or no autocorrelation. So we have to check that hypothesis. If we go to the D table and we look into it, the D value, the upper range and the lower range are 1.681 and 1.452 at 5% for the four estimated parameter or 3 explanatory variables. It is the critical region 1.42 and 1.681, and as we can see that the value 1.2 is even lower than the lower range. So if we recall that diagrammatical representation, so here this was 2, this is the upper bound, this is the lower bound, and then this was 0. So this value is 1.4. So our value lies somewhere here. So that shows a presence of positive autocorrelation in our data. So that's the conclusion from application of Durbin-Watson D statistics. Now once we have that Durbin-Watson being discussed in detail, the next topic is Brush-Godfrey BG test, its theory and its application. So let's discuss that. So the BG or LM test, it's also called LM test. This test has certain advantages over the Durbin-Watson D statistic test. So this test allows us for introducing lagged values of the dependent variable also as an explanatory variable. If you recall the assumption of Durbin-Watson D statistic test, you can recall that it was not allowed in the D statistic test. So that's the advantage of LM test. Secondly, this test also allow for higher order autoregressive schemes such as AR2 and AR3. If you recall again, the Durbin-Watson D statistic does not allow for higher AR scheme. It was just valid for one AR1 autoregressive schemes, but this BG LM test does allow that for higher orders of autoregressive schemes. Then in terms of moving average terms of the error terms could also be used. Finally, the error terms equation in the BG or LM test can be written as error term being function of the first error term, the second lag value, and so on till the P lag values. So if you look into this particular construction of this function, you can see here that in Durbin-Watson we have just these two terms, but now we have these additional terms as well, so we can check for a higher order of autoregression as well in BG test. The null hypothesis is that the autocorrelation coefficient is equal to 0, all collectively equal to 0, or in other words, there is no autocorrelation of order P against alternative hypothesis that there is. So that's the null hypothesis, and we do check that. And then the BG test involves the following steps when we have to apply it. First of all, we have to run the model and we have to estimate the residual terms. So that's a straightforward task. Then we have to regress on ET on all the regressors. That's the explanatory variable, but we have also to include autoregressive terms in our model, and then we have to calculate R square of this regression. So it's in a simple word, you take all the variables, you run the model, you calculate the error term from that model, then you take that error term and regress it on all the explanatory variable, but this time you include the number of the autoregressive terms as well in the model on which you are regressing the error term, and you obtain the R square of this model. So once you obtain the R square of that model, what we do next, we have to keep few things in mind. This is a large sample test, so when we have a very large sample, in that case the value of n minus rho is n minus rho, that's the number of observation minus the order of autoregression, multiply with R square of the model which you obtain from regressing the error on the explanatory variables that follow chi-square distribution with number of autoregressive degree of freedom. So in simple word, when we have a large sample, we can assume, or we know that it's proven statistically that n minus rho times R square follow the chi-square distribution, and then this chi-square distribution can be used to check the null hypothesis of having no autocorrelation. So if we reject that null hypothesis, it implies that there is a problem of autocorrelation. If we do not reject H0, then we say that there is no problem of autocorrelation. There is an alternative way of applying this LM test as well, and that's using F test of this model. The model you obtain in the first two steps, you use extended F test, one with restricted model and the other with non-restricted model. We have studied that F statistic as well in the past. It's no need to repeat it here, but we can use that restricted and unrestricted F model, and we can go for selecting if we go for selecting the unrestricted model, then we can have that this is an evidence of autocorrelation in the model. Eviews do provide these two results directly, the chi-square and F statistics and their relevant probability value, so we don't need to be worried about it. So once Eviews do provide chi-square and F statistics, we can accordingly make a decisions about the about the autocorrelation presence and absence. Now, while applying LM test, one should keep in mind two important things. The first thing is that the variance of the error term and its lag values, that's the error term of order 1 and of order 2, must be homoscedastic, or in other words, to apply LM test and have the results trustworthy, we have to ensure that our data do not have a problem of heteroscedasticity. So the heteroscedasticity problem has to be removed before applying a test for autocorrelation. Otherwise, we cannot trust that autocorrelation test results of LM test. And for doing that, all we have to do is that we can run wide robust error terms test procedure rather than applying the ordinary least square method. So that will solve the problem. We have discussed the wide robust error terms heteroscedastic fixed error terms process in our previous week classes. The second issue with this method is the practical problem in application of the BG test, and that's the choice on the number of lagged error terms. Now BG test step 2 was that you regress the error term on all explanatory variable and then the lagged error terms. Now lagged error terms could be from adding only 1 lag or 2 lag or 3 lag or 10 lag or 12 lags. So that's a subjective thing. So that make it practically difficult to pick a lag value, that how many lags should be added in a regression model. So normally we says that the lag values or the order of auto-regression or the row value depends on the type of SM series. Normally for monthly data we include 11 lagged error terms, for quarterly 3 lagged error term, and for annual we may add 1 lag error term. So this is the standard rule of thumb. When you have annual data, you just include 1 lag in the second step of applying this LM test. If you have a quarterly data, you add 3 lag, or for monthly you can add 11 lag, and then you can proceed with applying this test. However, another way, which is this is just the guideline, but in generally what we do is that we try applying number of tests and number of trial and error basis. We find the optimum lag value while ensuring the lowest AIC or SIC criteria for and also the level of significance of the error terms in the model in which we using the residual being regress on explanatory variable and the error lag values. So that was the BG test, and now we move back to the applications of the BG test. So the application of BG test, could be applied. So I name it practical task 13.4. You have to take the same data of autocorrelation which we have been using earlier. You have to run the model, the same model, you run it, the two variables explanatory in log form, the dependent variable also in log, and then the real interest rate to check autocorrelation using LM test or BG test. We follow the following procedure. We go to the results window, then we go to the residual diagnostics, then we select serial correlation LM test, and then we select lag. So we select lag 1 here. The question is why we will select 1. We will select 1 because it's in annual data, so it's good to start with 1. Otherwise, if it would have been monthly or quarterly data, we would have used 11 or 3, etc. So we press OK and we get the results. So the results is shown, but before going the results, I would request you that you do apply this test by yourself in Eviews, and then move to the result part and compare the results and have a discussion with it. So I'm going to apply this in Eviews as well. So let me switch to my Eviews and let's see how it works. So this is the result of the model which we have estimated earlier. Now you can see log of consumption was regressed on log of personal disposable income and log of wage, real personal disposable income, and real interest rate. Now we have to apply LM test. So we go to view, then we go to residual diagnostic, and then we go to serial correlation LM test. We click OK. We select the lag value 1, and then we press OK. and that gives us the result. I'm going to take this window to my discussion and we discuss it there. So this was the result we obtained from Eviews while running LM test or BG LM test. So we focus on first the chi-square part. Look at here the number of observation multiply with R square, and this is statistically significant at 2%. Look at F statistic. This is also statistically significant at 2.50. So H0 was rho 1 is equal to rho 2 is equal to all rho is equal to 0, or there is no autocorrelation of order Q. And then the H1 was that there is autocorrelation. And if you see here, you can see the output as well, different variables, their coefficient, their standard error. So the comments, both chi-square and F statistics confirm that there is a problem of autocorrelation. So the statistical significance of the first lag here, if you look at here, the first lag being included in the regression when the residual was being regressed, that was the step 2. So the residual was regressed on all explanatory variable and the error term. So we can see here that this is statistically significant as well. So that also is an indicator that the residual is correlated with the previous value, first lag only. Now you may try using 2 or 3 lags. Like we just use 1 leg, but you can try with second and third leg also. And you can see here, you will get R is reset -2, -3, and you can see their statistical significance as well. And among all these 3, you can select the one which has the lowest AIC or SIC value. As per the author of the book, he did tried it, but apparently with the first lag model was excellent performing or having the lowest AIC value. So that's why it says that okay, the first lag is better. So the conclusion from this is that there is a problem of autocorrelation and it's of the order 1. Now, once we have all this discussion, let's go back to the original slide. To sum it up, we discussed number of ways through which we can detect autocorrelation. This include one graphical method which has 2 sub ways through which we can do that. And then we have the run test. These 2 are not a very standard procedure, so not very reliable. Mostly Durbin-Watson D statistic, the third method, and GB LM test, the fourth method, are more commonly used. However, we have seen application of graphical methods. We have seen how run test work. We saw the theory of it. We also discussed the Durbin-Watson test in detail and also the BG LM test in detail. We also saw their application in Eviews as well. So with that, we come to the topic end of this week. I hope you had a good learning session, and now you have a clear idea of autocorrelation, what the problem is, what are the causes of autocorrelation, what are the consequences of autocorrelation, and how we can detect for autocorrelation. In next week, we are going to see some remedial measure for fixing the problem of autocorrelation. Hope see you in next session. Thank you very much for your time and patience. And if you like all this learning, please like my videos and subscribe my channel. Thank you very much.